Good morning, everybody, and welcome to the .nano Exploration Series. My name is Mark Galker. I'm an Assistant Division Head in the Advanced Technology Division at Lincoln Laboratory. So we're very pleased to have a talk this morning by Reggie Wilcox, who is a PhD candidate in the Electrical Engineering and Computer Science Department on campus and a research assistant at Lincoln Laboratory. He'll be presenting a talk on solid-state Ruby magnetometer. So Reggie is working on his PhD in solid-state quantum sensors with Dirk England in EECS and Daniel Brady here at Lincoln. He completed his BS in electrical engineering at Caltech and a master's in EE at Stanford. In addition, Reggie has industrial experience at Raytheon and Haystack Observatory. Reggie's been a great addition to the lab. Besides bringing his technical contributions, he's also very active in the community out here. He recently taught his fellow group mates how to curl. He's also an avid kite flyer and avid home improvement person. Just a few other housekeeping items before we get started with the talk today. So let's hold all of our questions till the end of the talk when we open up the Q&A session. And there's a couple of ways that you can ask questions. You can either raise your virtual hand and we'll recognize you and you can ask your question in person, or you can type it into the Q&A and we'll read it for you. So with that, Reggie, can you take it away?
Thank you for the great introduction, Mark. I'm Reggie Wilcox, and I'm here to talk to you about a solid-state Ruby magnetometer. So for today, I'll be starting with a brief history of magnetometry, and then move on to how the solid-state Ruby magnetometer that I've been working on functions. I'll then discuss how I optimize this sensor for magnetometry, and then get into some of the future directions for this project. So let's start with a little history lesson. Mankind has been fascinated with magnets for millennia, but it wasn't until around 400 BCE that the first real magnetic field sensors came about in China. This was called a directional spoon, and it consisted of a piece of magnetite, which is a naturally occurring magnet, that had been formed into a spoon shape and floated on a pool of water, and this would align itself along magnetic field lines. More than 1,000 years later, we had the introduction of the first real compasses, which used artificially magnetized iron needles. These could be used for navigation and unlock the age of exploration. At this point, the sensors would detect magnetic field direction, but we didn't have anything to determine what the strength of these fields were. In 1600, William Gilbert published De Magnete, which was a detailed phenomenological study of magnets, and this greatly furthers our physics understanding of magnetism. By 1860, we had a complete quantitative theory of magnetism, thanks to experimental work by Biot, Savart, and Faraday, which culminated in Maxwell's famous theory of electromagnetism. At this point, the best magnetometers were mechanically based and were developed by Gauss and Weber, which saw use well into the 1900s. By now, magnetometers could detect field strength as well as direction. In the 1960s, we saw the advent of atomic magnetometers, which used the internal quantum energy level transitions of atoms in order to determine what the applied magnetic fields were. These crucially relied on lasers for both state preparation and for readout, and were not operated at room temperature. In the late 1990s, nitrogen vacancy centers in diamond were demonstrated as magnetometers using optically detected magnetic resonance at room temperature. And even though there has been recent work using microwave readout of this sensor, it still crucially relies on a laser for state preparation. That brings us to today, where I'm talking to you about a Ruby magnetometer that operates at room temperature using no lasers and offers a 10 picotesla per root hertz sensitivity. To understand why the sensitivity is important, we need to look a bit at the magnetic field scales that we would want to be sensing. You can see around the picotesla level, there are a lot of interesting technological and biomedical applications where you may want to use a magnetic sensor. And for biomedical applications, it's particularly important that they can operate at room temperature because these sensors come in close contact with skin. Using solid-state sensors has many advantages, but a few drawbacks. The measurements can typically be tied to fundamental physical constants, usually the electron gyromagnetic ratio. They also don't require any vacuums or cryogenic components, and they can often be interfaced to using commercial off-the-shelf microwave technology. One major drawback is they typically require a laser for either state preparation or readout, which can drive the power and size budget of the system, as well as present many challenges for development and integration. Largely due to the use of a laser, the size, weight, and power requirements of these sensors can be rather large, and material fabrication of these solid-state sensors can be time-consuming and expensive, especially in NV diamond, which has a very slow growth process. Ruby does not have these drawbacks. It has a 10 picotesla per root hertz sensitivity with no cryogenics, no lasers, and an efficient growth process. We can see on the right here a comparison of the Ruby magnetometer against some of the best NV magnetometers. Being lower on this horizontal or this vertical axis means you have a better sensitivity. So you can see while the Ruby is not the best in terms of sensitivity, it offers many advantages in terms of eliminating some of the drawbacks of solid-state sensors. A particularly important comparison is to the work by a former student in my group, Eric Eisenach, who did the microwave readout in NV diamond. This uses a very similar readout technique to what I'm using, so it provides a good point of comparison for this technology. To understand why I'm looking at Ruby as a sensor, we need to look at how the modern technology developed here. In the 1940s, we saw the introduction of atomic and NMR systems, which were passively initialized. This means that the system was left to thermalize, and you had a natural polarization due to the Boltzmann distribution in the sensor. In the 1960s, lasers were developed, and these could be used to initialize and read out these systems, which led to vapor cells and SURFs. This allowed the dramatic improvement in the technology and has made some great sensors that are used to today. In the late 1990s, early 2000s, it was discovered that you could do this same active initialization using a laser in NV diamond, and that has spurred a tremendous amount of research, which has led to a lot of phenomenal applications of this. However, that's left this space of solid-state sensors with passive initialization relatively unexplored. So that's where my Ruby work fits in. It's my hope that this Ruby sensor serves as a proof of concept to demonstrate that you can make a passively initialized solid-state sensor, which I'm hoping will spur some research and development into using new materials to perform sensing, such as silicon vacancy or dye vacancies in silicon carbide. This could lead to optimized performance, since it's unlikely that Ruby is the optimal material to be used for this type of sensing. You could also look to unlock additional sensing modalities, such as electric field or strain sensing. And you could even look towards using specific tailored energy levels for certain applications where you may want to transfer spin from one system to another. Now we'll discuss how Ruby itself functions as a magnetometer. So Ruby is a sapphire crystal, Al2O3, with chromium 3+ ions substituted for aluminum in the lattice. It has a trigonal crystal system, which results in a birefringent material, meaning that there's a different permittivity along the extraordinary and the ordinary axis. The extraordinary axis is particularly important in this work because it serves as the quantization axis, the quantization direction used in the when we look at the Ruby Hamiltonian for the chromium ions. Here we see in the energy level diagram from the Hamiltonian for the chromium ions. There are three important points about this energy level diagram. First is that there is a zero field splitting of around 11.5 gigahertz. This is large enough that we can allow for thermal polarization at room temperature, while still being in the microwave region where we can get commercially available products to interface and interrogate these spin systems. The eigenenergies also depend linearly on the magnetic field when it's applied along the extraordinary axis, which is this dependence that allows us to perform magnetometry. And finally, we can selectively drive one of these transitions spectroscopically by applying a bias field. There are only three allowed transitions in this system. The first, the +1/2, -1/2 transition, will occur in the tens of megahertz region for any bias field that we're using in this work. So we can effectively ignore this transition. The other transitions, the +1/2, +3/2, and the -1/2, -3/2 transitions have an opposite dependence in magnetic field, which means that they'll split in different directions when we apply the bias field and allow us to spectroscopically drive a single one of them. So for NV diamond uses a active initialization scheme using optical polarization. It uses a laser to excite the spin states, and through an asymmetric decay process, preferentially populates a single spin state. This can result in a state preparation efficiency of about 80%. And in the work done by Eric, that resulted in 10 to the 15 polarized spins. By contrast, in Ruby, I use a passive scheme that we call thermal spin polarization, which uses the energy difference in spin states due to the zero field splitting to preferentially populate the lower energy state via the Boltzmann distribution. This only prepares about 0.05% of the spins in the with polarization, but we can still achieve close to the same number of polarized spins, about 3 × 10⁻⁴, even though we have only such a small percentage of polarization. There are two reasons for this. First, as you'll recall, I mentioned that Ruby is has a much more efficient growth process, so we can get much larger samples of it and use that for magnetometry. And furthermore, the chromium defects in Ruby are about 100 times as dense as the NV defects in diamond, which allows us to get this high of polarization with just thermal through thermal means. The cavity readout technique that was used by Eric and in this work applies a drive microwave at a frequency omega d that interacts with the spin system, and we measure the reflection coefficient to see what the spins are doing. If the microwave photons were just to interact with the spin system, there would not be sufficient interaction to produce a measurable result in the reflection coefficient. So what we do is use a high Q dielectric resonator, which mediates the spin photon coupling by increasing the lifetime of the photons within the cavity. Once this is done, the spins interact strongly enough with the microwave photons to produce a measurable effect in the reflection. In the work done by Eric, he used an external dielectric cavity to make the high Q system. But in Ruby, since we can make much larger samples, the Ruby itself is fashioned into a high Q resonator near 11.5 gigahertz. This also has the added benefit of increasing the filling factor, which means that a higher percentage of the microwaves that are introduced to the system actually can interact with spins. This is placed in a copper shield, which reduces radiative losses and improves the Q, and microwaves are coupled in through this probe here on the left. You can see here, this is a schematic of the experimental setup, which behaves as a homodyne receiver. we take the microwave source, generates a signal, which goes through a 6 dB coupler and drives the LO port on an IQ mixer. The 6 dB reference arm goes through a variable attenuator, which is used to adjust the amount of power incident on the Ruby. We sample through a 20 dB coupler to monitor what the applied power actually is. Then the signal arm goes through the circulator, is delivered to the Ruby resonator. It reflects off, goes back through the circulator, is amplified, mixed down to baseband, and then the I and Q ports are digitized. I also have a bias coil here, which is used to produce the magnetic bias field that allows us to separate the plus and minus spin transitions. It also allows me to sweep the microwave field to probe the cavity physics. This test coil here produces a known 242 nanotesla field at 10 Hertz, which is used to measure the sensitivity of the device. So in Eric's work in Diamond, he derived this nice relation between the reflection coefficient and the physical parameters of the system. And even though this was done in Diamond, the Ruby system is exactly analogous. So by modifying these physical constant or physical parameters, I can apply this same model to Ruby. This first term in the denominator describes the interaction between the drive microwaves and the cavity resonance, and in the absence of any spin terms would be a Lorentzian. This next term is the interaction between the drive microwaves and the spin system, and this is the term that produces the dispersive shift that allows us to perform magnetometry. This last term we call the power broadening term, and it's actually detrimental to us because it limits the maximum amount of power that we can apply to the system. And I'll talk about this term a little bit later during the optimization step. To understand this reflection coefficient better, I do a 2D sweep over frequencies. This vertical axis is the drive microwave frequency, and the horizontal axis is the spin transition frequency, which is adjusted by sweeping the bias field. I can use this model for the reflection coefficient and fit this to the data and reproduce this reflection coefficient plot. You can see here there's a qualitatively good agreement between the experimental data and the fit. And I can also extract some physical parameters such as T1 and T2 from the system. And you'll note a reasonable agreement with previously published results. In order to actually perform magnetometry, I'm interested in a single 1D slice of this data where I vary the magnetic field, but keep the drive frequency fixed. You can, when I do this sweep, you can see the blue is the absorptive component of the data, while the dashed red line is the dispersive component. The sharp slope in this dispersive component indicates that there's a strong dependence of the reflected signal on the applied magnetic field, which is what we can use to do magnetometry. And it is this region where we want to operate the sensor. Next, we'll discuss how this is optimized. So there are two main parameters which need to be optimized: the applied bias field and the strength of the applied magnetic field. Sorry, the strength of the applied microwaves. So you can see here there's a optimal value in the applied magnetic field. This is around 31 Gauss, and this roughly corresponds to making the spin transition frequency the same as the cavity resonant frequency, as would be expected. Furthermore, this 31 Gauss corresponds to approximately an 80 megahertz resonance. And in the previous 2D reflection coefficient sweep, I estimated the spin line width to be about 40 megahertz, which indicates that this bias field is sufficient to resolve the plus and minus spin transitions as we would like. There's also an optimal applied microwave power. This may seem a little bit surprising at first, since you would imagine Increasing the power would continually improve your SNR and would result in a more sensitive device. However, there is phase noise on the microwave source, which since it's on the microwave source will scale with the applied voltage, meaning that the noise that you're introducing to the system also increases. And with the power broadening effect, causes the sensitivity to get worse at higher powers. To better see why there is an optimal power, I did some additional sweeps. Here we have the reflection coefficient versus the applied magnetic field. And you can see when we increase the power, the slope of this does continually get higher. However, because of this power broadening term, the marginal increase in this slope as the power is increased actually decreases. So instead of looking at just the slope of this, I look at what I call the normalized slope, which is just the slope of the signal divided by the applied voltage. So the slope of the signal would be proportional to the signal you get from a magnetic field being applied, and the voltage would be proportional to the phase noise. So this would roughly be proportional to the SNR of the system if we're considering only phase noise. And so that would then be inversely proportional to the sensitivity. So seeing we do see an optimal normalized power, or sorry, normalized slope at a 17 to 14 dBm, which indicates that increasing the power further is actually going to decrease our sensitivity. Now that we have the optimal optimal parameters for the system, I can do a full sensitivity measurement. This is found by just taking the value of the test coil, which is 242 nanotesla at 10 hertz, dividing that by the SNR of the system to get the sensitivity. So when this 10 hertz field is applied, this is the raw signal coming out. You can see the 10 hertz signal on here. This is Fourier transformed and appropriately scaled to get this projected sensitivity curve. And you see around 5 kilohertz, you get the optimal sensitivity of around 9.7 picotesla per root hertz. I also capped the circulator with 50 ohms to get the noise floor of the microwave electronics, and this levels out around 5 picotesla per root hertz. And we're ultimately limited by thermal noise at 1.1 picotesla per root hertz. Finally, I'll discuss some future directions for this work. So the most obvious future direction would be to improve the sensitivity further. I believe that the system is limited by phase noise, so using an improved microwave source would allow us to approach the microwave electronics noise floor of 4.8 picotesla per root hertz. From there, the microwave electronics would need to be improved, which could then allow us to approach the thermal noise limit of 1.1 picotesla per root hertz. From there, you need to lower the thermal noise limit, which is actually a property of the Ruby sample. So one option is to increase the number of polarized spins. The most obvious way to do this would be to use a larger sample of Ruby. But a little bit of care does need to be taken when doing this, since the Ruby itself is a high Q resonator at 11.5 gigahertz. So you need to make sure that the larger size still has a high Q resonant mode at a suitable frequency. The other method would be to cool the sample and increase the polarization percentage. This would obviously require additional components and increase the complexity of the system. So some analysis needs to be done to see whether this is a viable trade-off between sensitivity for specific applications. The final method would be to improve the spin line width. So the spin line width in Ruby is thought to be dominated by 27 aluminum nuclear interactions with the chromium ions. So a slow RF drive may be able to decouple these two systems and improve the spin line width, but it's unclear whether this would actually be a viable path forward. Some other exciting improvements would be using a pound driver Hall style locking mechanism where the microwave source would be locked to the cavity resonant frequency, which could help to mitigate phase noise at low frequencies. This would also allow some control over the shape of the noise, which would allow you to put the low noise band at the frequency of interest for your sensing application. Another really interesting improvement would be to use circularly polarized light in order to remove the DC bias magnetic field. So right now, all the DC bias magnetic field is doing is separating the plus and minus spin transitions. But since circularly polarized light also has an associated angular momentum, we could use this to selectively drive one of the transitions by angular momentum instead of by frequency. This would be beneficial for low frequency magnetometry, where any noise on the DC bias field is going to show up directly on your measurement and ruin it. The final option would be using this for full vector magnetometry. Since the sense magnetic field is small compared to the DC bias field, these sensors actually perform a projective measurement along the DC bias field, meaning that they operate as vector sensors. So by using 3 orthogonal sensors, we could do a full vector magnetometer. However, this crucially relies on the use of a DC bias field, so it's unclear whether this would be compatible with the circularly polarized improvement. So I'd like to thank everyone for listening to my talk this morning, and thank the quantum sensing group out there, especially my advisor there, Danielle Bragi, with special thanks to John Barry and Matt Steinecker for their guidance and support on this project, as well as thanks to my advisor, Dirk Englund on campus. So that concludes my brief history lesson and leaves us at present day with a Ruby magnetometer with no cryogenics and no lasers. Thank you.
All right, Reggie. So thanks very much for that great talk. Okay, so it's open for question now. And again, as a reminder, you can either type it into the Q&A or you can raise your hand. It turns out that we have one of each at the moment. So let's start with the Q&A. So we have a question from Philip Nikolaev, and he asks, can nitrogen vacancies be introduced artificially in diamonds in a controlled manner?
I don't know if it depends on what you mean by a controlled manner, because it is a fairly random implantation process where it's used in the nitrogen's introduced in the growth of the diamond to incorporate it. And then you need to irradiate the sample to create the vacancies. And then those, when it's annealed, those come together. So you can kind of control the depth of them, but there's not a whole lot of control as to exactly where those are placed.
Right. So I imagine maybe the doping levels, can you control that?
Yep. You can control how the doping level of it. So yes, you can control what percentage of NV you get in there.
Right.
There are trade-offs with how much you put.
Okay, great. Okay, so then let's go to the raised hands. So the first question is from Sarfraj Khan.
Please explain the working and principle of vapor cell magnetometer.
Oh, you have some noise in the background. Did you catch it that time, Reggie?
I think he said explain the working principle of vapor cell magnetometers.
Okay.
So that's a little bit tangential to the talk, but those are basically probing the quantum energy transition in the vapor cell, or in the in usually like a heated gas, which then you can probe that using lasers to figure out what the applied magnetic field is.
Okay. So then let's go back to the Q&A. And so we have a question from Robert Roth. Do you plan to commercialize this technology?
We don't have any plans to commercialize it at this time.
So this is Eric Thompson from Lincoln Laboratory. I guess, how does the size of this compare to like flux gates or things of that nature? I know we can get pretty small vector sensors from flux gates. How would this eventually compare to those in size? Or are we trading swap for sensitivity here?
This can get to a fairly compact sensor. So this is this whole sensor on the right here is this whole cavity is about I think it's around 5 centimeters across. So you could design this to be fairly compact. It's right now the main size for this sensor is actually in the applying the bias field and the microwaves, but that can be easily miniaturized.
All right, thanks.
Okay, so back to the Q&A. So question, you suggest that this work is a stepping stone, that is Ruby isn't going to be the implementation. Did I understand that correctly? To be more specific, do you have an envisioned, or what do you envision this will end up looking like in a practical application, say in minerals exploration?
So the reason we say that Ruby is probably not the optimal material for magnetometry is because of the large spin line width in it. So I don't have a vision as to what the optimal material in the end would be, but I think there's a lot of materials that have not been tried in this kind of context that we could explore further and perhaps see if they do provide a useful magnetometer for certain applications.
Right. So just to follow that up, how well cataloged are the the materials properties so that you can search for a more optimal? So I'm guessing that you're coming up with a pretty good sense for what properties you're looking for in the atomic structure in the Hamiltonian. And can you sort of figure that out just by looking at data sheets, or do you need to have some more in-depth simulation tool to do a broader survey to find a more optimal material?
So there are a couple of parameters that are important to be able to do this. One, you need to have a suitable zero field splitting to get this thermal polarization. You want to have a low spin line width. And you actually need to have a low loss material in order to do this. So if you look at the parameters of Ruby, because of the spin line width, it actually doesn't look like it should be that good of magnetometer, but because sapphire is such a low loss material, you can get a very high Q sensor out of it, or a high Q cavity. So that is a one property that made it perform better than would be expected based on just some of the line widths alone.
Okay. Okay, and then let's go back to the raised hands. So we have Juan Herbersomer.
Yes, hello, can you hear me?
Yes.
Okay, so yeah, this is, thank you for the good presentation. This is Juan Herbersomer from Texas Instruments. So my question here, when I look at this and I compare the solid state, always compare that with the vapor cell approach, the first question that comes to my mind, how this can be so good, okay? Because the fundamental question here is the following, okay? So, in the vapor cell type of devices, you get extremely high quality factors because you can keep essentially the quantum coherence very good because of the very low interaction between the atoms with the other atoms, correct, in the cell. When you work at low pressure, and pressure broadening essentially can lead you to really sharp. If you work at low pressure, can lead you to sharp high quality factors. But in the solid state, one of the things that I always cross to my mind is, well, it's so close to the other atoms, okay, that the interactions with the next neighbors, it made me to think that you will lose the quantum coherence pretty quickly there. Okay, now what in essence, okay, if you can explain how actually you solve this question or this actually apparent inconsistency, okay, and what are your numbers, for example, for what type of quality factors you have, and how you can explain this I don't know if you understand my question, this kind of difference,
I don't know if I have a great answer for your question, but I think so when you're talking about the quality factor, I assume you're more referring to how long the more like the quantum coherence time, as opposed to like the quality factor that I'm talking about with the like of the microwave cavity. Is that correct?
I'm talking about the quality factor of your quantum transition, okay? I mean,
Right. Yeah.
That's what I'm talking about, yeah. Because at the end of the day, it's about quality factor and SNR, correct? Is how sharp is your transition and how good is your SNR. I mean, if your quality factor is not that good, but your SNR is super good, okay? You can equilibrate that and make a really good quantum device. But I don't understand how come here, okay? You have so close next neighbors, and essentially your interaction is so strong, and you still can get such a good numbers, correct? That's my question.
So I think what one of the benefits that you get with a solid state system, so they are packed closely together, and so that kind of leads into the spin line width that I talked about earlier of like it's about 42 megahertz for here, so it's a fairly broad spin line width, and that's because they are so close to each other. But on the opposite side, because they are so close to each other, you can just you have so many more spins that are actually interacting. So I think it's the fact that you can interact with so many of these spins, even though they don't have the longest coherence, that allows you to get a good sensitivity.
Okay, so just to clarify, so then you have 42 megahertz quantum width at 11 gigahertz. Okay, so that's how I can calculate your quality factor.
Yeah.
So, and your SNR, how good is your SNR?
I don't have that number on the top of my head. I believe it's close to, I think it's on the order of 100.
Okay. Okay. Thank you. Thank you.
Okay. So another question, Rohan Han.
Yes, thank you for the great talk. I just have some curiosities about removing the DC bias using the circular polarized wave. So can you make some more comments on that? In particular, would you have trade-off in sensitivity if you use a circular polarized wave without DC bias?
So, you know, in theory, you should not have a reduction in it. So in theory, you should not have a reduction because of that. But I think stuff like, you know, if you have, you know, a mismatch in, like you generate circular polarized by having, you know, a 90-degree phase shift and driving it with two microwave probes. So that, you know, if you have any phase mismatch between those two, all that's going to, you know, create some of the wrong polarization for you. So you would have a reduction in the isolation between the plus and minus transitions a bit. But other than like implementation details, I don't believe you should have a decrease in the actual performance of the system.
Thank you.
Okay, so that looks like all the questions. So again, Reggie, thank you for the excellent talk. Very engaging. It looks like very, very interesting work. So we wish you well as you continue the work towards your thesis. And I want to remind everybody of the next seminar. So this will take place on Tuesday, October 11th by Shibi Chen from the EE and Computer Science Department. So hope to see everybody then. Okay, take care.